Okay, so we are back and we are going to continue today with our area approximations. And before I get to that, let's go over number 29, which was homework from last night. So this is 4.2, number 29, and we had f of x was equal to 2x plus 5, and we're looking on the interval from 0 to 2. Alrighty, and so I believe I asked for, was it, let's see, for an infinity number? I can't remember, to be honest. I think that's what the homework was. Um, so let's just go with that. Alrighty, let's think about what this looks like before we get started. I always like to have an idea of the function. So 1, 2, 3, 4, 5, 6, and not going to be to scale 2, 3, 4, 5, 6, 7, 8, 9. Alrighty, it hits at 0, 5, because that's the y-intercept, right? So 1, 2, 3, 4, 5. And then it has a slope of 2, so up 2 over 1. Like I said, this is not what it actually looks like. And this is up 2 over 1, so something right about there. And so I got this function right here, and we're looking at the area right here. Okay? Alrighty, so, and if this is at 1/2, this is 1, and this is 3/2, for no reason. Alrighty, so, if I want to break this into 4 rectangles using the right endpoint, so my width, hold on, let me actually do that. If n equals 4, the width is going to be, well, b minus a, so 2 minus 0 over the number of rectangles, 4. So each one is going to be 1/2. So since it's the right endpoint, I go up using the right side of the rectangle, go over, the right side of the rectangle, go over. Not all the way like that though. That's funny. Like this instead. Alrighty. And then all the way up and over. And finally all the way up and over. Assuming I can draw and all these are the exact same width. So now that we have this, we can think about R1, R2, R3, and R4. So let's go ahead and write that down. I think I can fit it in right here. So R1, R2, R3, and R4. Let's do the rectangles first. And so this one is R1, R2, R3, and R4. Okay, so what do I need to find these areas? Well, I need the width, which I already have. And then I need the height. And just multiply them together for the area, right? There's the height, and this will be the area. Okay, so in the case of R1, the width we've already calculated is going to be 1/2. And the height is going to be, well, I'm going to feed the right endpoint in. So this is going to be f of 1/2, which is going to be 2 times 1/2, which is 1, plus 5, which is 6. So I get 1/2 times 6, or 6/2. Okay? And we'll leave it as halves for right now if I want to be able to add up all the odd ones. So for R2, again, the width is 1/2. And then how high up does it go? Well, it goes, I feed in x equals 1 to the function. So f of 1, well, that's going to be 2 plus 5, 7, which means that the area is 7/2. Okay. There I go to R3. R3, 1/2 is the width. Rectangle, well, I'm going to feed in 3/2. Okay. When I do that, I'm going to get 2 times 3/2, so that'll be 2 plus 5. Sorry, 2. Whew, 3 halves times 2 is 3, plus 5, which is 8. And so 8 times 1 half is 8 halves. Okay, and then finally, last one, 1 half. And what do I feed it? I feed it the right endpoint, which is, I feed it 2. So 2 times 2 is 4, plus 5 is 9. Alright, so that's going to be 9 halves. Alrighty, so the total area is going to equal, for these rectangles, which this is still just an estimate, so I'm definitely going to put an approximation sign. So I'm going to have 6 halves plus 7 halves plus 8 halves plus 9 halves. And let's see, 13, 21, 30. 30 halves, which is 15. All right, so that is the estimate using just the rectangles and kind of getting an estimate from them. But now let's clear this and let's do the right endpoint formula. Figure everything out using that. So I think you'll like this way better. I enjoy this way. It's something about it is actually satisfying to make rectangles. Some of my students have even come in and said that they actually really enjoyed this part, not so much the math part. So, that's okay. If it makes you happy, that's all good. Let me clear this, but let's do the right endpoint formula. So the right endpoint formula that we came up with yesterday looked a little bit like this. The area is approximately the sum, I from 1 to n, of, well, this one was the width, so it's b minus a over n. And then the height is, I feed in what? F of b minus a over n times I. Because when it's like in the previous example, the very first rectangle where I was 1, we fed in f of 1 half, which is exactly what we'd get, b minus a divided by n, that would be a half. When it was the second rectangle, we fed in 2 halves, which is what we'd get when I is 2, then 3 halves, and then 4 halves. So this is the formula that we can use to figure out those values. What I want to do now is the math behind getting this into a general formula, and once we have that, we can then plug in n equals 4, n equals 8, and take the limit as n goes to infinity. So let's see how we get that general formula. First off, for this very specific case, we're going to have b minus a, so the width for this specific function over that specific interval is 2 minus 0 over n, which is going to be 2 over n. Okay? Now the height is a little bit trickier, but it's not too bad. Okay? I've got f of x is equal to 2x plus 5. Okay? So what would f of, this is going to be 2 over n times I. What would that give me? Well, that would be 2 times 2 over n I plus 5. Just like that. Okay? That is literally what I get when I plug in b minus a over n times I into my function. Does that make sense? This piece right here gets substituted. So this is an x. I mean, this is an x, so this goes in where that x was, which is right here. F of x is 2 times x plus 5. F of 2n times I is 2 times 2n times I plus 5. So just straight composite function work, or this is F notation actually. We haven't even done composites in a long time. So this is just F notation. And so this is actually equal to 4 over n I plus 5. Okay, so my area is going to approximately equal, I'm going to have my summation I equals 1 to n of my width, 2 over n times my height, which is going to be, when I feed it into the function, I'm going to have 4 over n I plus 5. Okay, so I've got it all set up now. First thing I'm going to do is move this 2 over n outside the summation because it has no i's inside of it, and n is a constant for our purposes. So it's going to, I can shift it across the summation. So I can say it's approximately equal to 2 over n times the summation I equals 1 to n of, well, what's left? 4 over n I plus 5. Okay, now this is equal to 2 over n times, here we go, big bracket. I can move the 4 over n on the outside of the summation. I equals 1 to n, and what's left? I plus summation I equals 1 to n times 5. So what I did is I broke it into two separate summations, and I moved the 4 over n, which is, it can see as a constant, on the outside. Now by doing that, I can now use my formulas. I know what the summation from 1 to n of I is equal to, and I know the summation of a constant, how to evaluate that. So my area is going to be approximately 2 over n times, we're going to have big bracket, 4 over n, and what does this evaluate to? Well, this evaluates to n times n plus 1 over 2, that formula, plus, my dogs are going crazy outside, weird. And now I've got this piece right here. What is the summation from 1 to n of 5? Well, it's the number 5 added to itself n times, which is just a total of 5n. Okay? So now I have 2 over n times, I'm going to have 4 over n times, well, this is going to give me n squared plus n over 2, not bad, plus 5n. Okay? So far so good. We're getting there. Okay? I'm now going to distribute this 2 over n through. So it's going to be equal to approximately 2 over n times 4 over n is 8 over n squared times n squared plus n over 2, and then 2 over n times 5n. Well, the n's are going to cancel. I'm just going to be left with what? 2 over n times 5n gives me 10. Is that right? 5n, no? I'm sorry, I lost my place. 5n, my dogs are distracting me. 5n times 2 over n, the n's cancel. I'm left with 2 times 5, which is 10. Okay? Now, I can go from there. This is looking a little bit strange, but I think it'll all work out. I've got faith that it will eventually work out. So let's see what we have now. So I've got 8 over n squared. I'm going to distribute through this. So 8 over n squared times, well, first off, I can simplify, right? That 2 will go into the 8 4 times. That's nice. So now I'm going to have 4 over n squared times n squared, which is going to be 4. And then 4 over n squared times n is going to be 4 over n plus 10. So the final value is going to be 14 plus 4 over n. Whew. And what is that? That is our area approximation. And it may seem like we had to do a lot of work to get here, but it's worth it. All this is just algebra, but it's a lot of nitpicking algebra. You have to be very careful with it. But now that we've got this formula, let's actually use it. I think it will be kind of nice when you see how it works. So let's clear this and go and knock this out. So clearing that. So I have my function was f of x is equal to, what was it, 2x plus 5. Yeah, 2x plus 5. And then I found that the area is approximately equal to, I had 14 plus, what was the last part? 4 over n. Okay, 4 over n. Alrighty, so let's let n equals 4. So n equals 4, we're going to have the area is approximately equal to 14 plus 4 over 4, which is 14 plus 1, 15, which is exactly what we found when we added up the rectangles. Okay, let's let n equal 8. Area is going to approximately equal 14 plus 4 over 8, which is a half, so 14.5. Okay, so as the number of rectangles gets greater, it's going down. The area estimate is going down, which makes sense because it's going to more closely approximate the actual curve. There's less excess on top of the curve. So now let's take the limit as n goes to infinity. So the area as, don't go the approximate anymore, equal to the limit as n goes to infinity of 14 plus 4 over n. Well, that limit, I can evaluate it right off. That goes to 0. The actual area is 14. Boom. Not bad. So if I did an infinite number of rectangles and added all the little areas up, I would get 14 as my limit. Pretty cool. I like that. So hopefully this wasn't too bad. I know you're still getting used to how to use the sigma notation formulas, convert them into n's, and then do all the simplifications so that you can get this expression right here, this nth approximation for the area. So let's do another one. Let's practice a little bit more. I'm going to clear this, and let's get started. If I can clear. Okay, for the new function, let's look at f of x is equal to 3x squared plus 2x. And it sort of looks like that. Takes off really fast. So that's kind of what it looks like. You can look it up on Desmos if you want. But let's see. First things first, I've got this function, and I want to go from, let's say my interval will be from 0 to 2. Okay? So my a is 0 and my b is 2. So that means that my width is going to be b minus a over n, which is 2 minus 0, which is 2 over n. So that is going to be my width. Now, I've got the width, I need the height. Okay, how do I get the height? Well, I get the height by feeding in my x-coordinate that is going to increment each time I go to a different rectangle. So remember the formula for that is, gosh, I guess I can put it right down here. The area is equal to the the width, which is b minus a over n times the height, which is f of b minus a over n times I. Okay, so for the height now, it's going to be 2 over n I. Well, what will that give me when I plug it in up here? Well, when I plug in 2 over n I, I'm going to get 3 times 2 over n I squared plus 2 times 2 over n I. Okay, so that's going to be my height, this thing right here. So what does my area look like? Well, my area looks like I'm going to have the width. Oh, hold on, let me do my summation. Summation I equals 1 to n of the width, 2 over n, times the height, which is all this up here, 3, 2 over ni squared, plus 2, 2 over ni, bracket. Alrighty, so that is my area, and I should do an approximation for that. Until we go to infinity, it is an approximation. So I got a lot of algebra to clear up here, but that's not too bad. So this is going to approximately equal to, I'm going to move the 2 over n out to start. I equals 1 to n, and then I'm going to have 3 times, well, this in here is going to be 4 over n squared, so it's going to be 3 times 4 over n squared is going to be 12 over n squared, I squared, like that. Okay, and then over here I'm going to have plus 2 times 2 over n, it's going to be 4 over n I. Okay, it's already looking not so bad, right? So I've got this expression. Now I'm going to try to I'm going to distribute the summation through so I can isolate my i's. So if I do that, I'm going to get, the area is approximately 2 over n, and then I'm going to have one big bracket here, and it'll be, you know what, I'm going to do 2 steps so that it doesn't confuse anyone. So this is, I'm going to break it into 2 summations, I from 1 to n of 12n squared I squared, plus summation I from 1 to n of 4 over n times I. Okay, so this is going to equal 2 over n times, here we go, big bracket. I can move the 12 over n squared on the outside, so 12 over n squared, summation 1 to n of I squared, plus, I can move the 4 over n out, 4 over n, summation I from 1 to n of I, bracket. Okay, and I have a formula for what I squared is, and a formula for what I is. So I can apply those. We're going to have this equal 2 over n, and then it's going to be bracket 12 over n squared times, well, what does the summation of I squared look like? It's n times n plus 1 times 2n plus 1 over 6. Okay? So that takes care of that summation. And then I go to the next one, plus 4 over n times, what's the summation for I? Well, the summation for I is just n times n plus 1 over 2. Okay, and that's it. Bracket. So this is what we have, and I am going to, I really don't want to have to erase and rewrite, but it looks like I'm going to have to. All right, so just take a mental picture of this. I'm about to rewrite it on the next. So here we go. So I have the area is approximately, if I can actually write an A, is approximately, I had 2 over n times, big bracket, it was 12 over n squared times n plus 1, 2n plus 1 over 6, and then plus 4 over n times n plus 1 over 2. Okay? So, now that I've got that, I can distribute this 2 over n, if that sounds good. I don't have to. I can wait, or I can send it through. I'm just going to go ahead and send it through. It's approximately equal to, this is going to be 24 over n cubed times, what does this become? Well, let me do some scratch work. N times n plus 1, well, that's going to equal n squared plus n, and then n squared plus n times 2n plus 1 winds up being 2n cubed plus 3n squared plus n. Alrighty? So this becomes 2n cubed plus 3n squared plus n over 6, and then plus, now I have to distribute this 2 over n times 4 over m. That is going to give me 8 over n squared times n plus 1 is going to be n squared plus n over 2. Alrighty, we're almost there. So now I can distribute this and make it, again, simplify it first. The 6 makes out a 4. So I have 4 over n cubed times 2n cubed. The n cubes are going to cancel. I'm going to be left with 4 times 2, which is 8. And then 4 over n cubed times 3 n squared. Well, 4 times 3 gives me 12. And then it's over n. That's what's left. So 12 over n. And then 4 over n cubed times n is just going to be plus 4 over n squared. Alrighty, so that's this part. Then over here, I can simplify it again. There's a 4. So I'm going to have 4 over n squared times n squared. So that's going to be 4. 4 over n squared times n is going to be plus 4 over n. Alrighty. So far, so good. So now I can combine all of these pieces. And let's see what I'm going to get. Let's see. That looks strange. Did I do that right? 4 times 2 is 8. 4 times 3 is 12 over n. 4 times n is 4 over n squared. And then that just looks strange for some reason. I don't know why. Alrighty. I am worried that I did something differently. It'll be alright. Let's see how it works out. So right here, I've got, okay, so I've looked at it deeply. I paused for a second to make sure I did all the math right. I don't want to make any mistakes here at this point. So I get, this is equal to 8 plus 4, which is 12 plus, I've got 12 over n plus 4 over n, that's going to be 16 over n, and then plus 4 over n squared. Alrighty, so let's let n equal 4. What would we get if we did 4 rectangles? Well, we would get 12 plus 16 over 4 plus 4 over 16. So this is going to be 1/4 plus 16/4, which is 17/4. So this is 12 plus 17/4, which that'll go in 3 times and 3/4. So this would be, is that right? 4 times and 1/4. 4 times and 1/4. So that's going to equal 16 and 1/4. So 16.25. Okay. Now, if I do 8ths, so let n equal 8, well, I'm going to get 12 plus 16 over 8 plus 4 over 64. So this is going to be a big mess is what it's going to be. I've got to convert it to 64, so 16 times 8. What is that? 8, 428. I think that's right. So it's going to be 12 plus 128 plus 4 is 132 over 64. I think that's right. And so if it's not exact, that's okay. I'm not too broken enough to mess up a little bit with the math. So this is going to be 14, and let's see, that's going to be 4, 128, yeah, 4 over 64. So, gosh, I hate to do mixed numbers, but I don't want to do 14 and 1/16 when the dust settles, I think. I don't want to do that. But as you can see, it went from 16 and 1/4 to 14 and some change. So now let n approach infinity. Well, that's going to be the limit as n goes to infinity of 16 over, my gosh, so they're looking right at it, wrote the wrong one. 12 plus, I'm going to have 16 over n plus 4 over n squared. 16 over n, 0. 4 over n squared, 0. What is the actual limit? 12. There you have it. That is what we believe to be the actual area. It is the actual area. I verified it. So, not too bad. Now that we've done another example, hopefully it's starting to feel a little more comfortable, and we can move on to something a little bit trickier. Not a whole lot, just a little bit. All right, so I'm going to clear this, and let's get started with the tricky part. Just keep in mind 12. Okay, that's what we got for that one. Just store it somewhere. So what we've been doing up till now has been using the right endpoint. So all the rectangles are based on the height of the right side of the rectangle. So let's bring back our good friend function, f of x equals x squared. Graph it up a little bit. Something like that. And we'll call this 4, 3. Oh boy, that's like way closer to 3. That's okay. If I can actually write, it would help a lot. 2 and 1. Alright, we'll say that those are even. Now, the way we were doing is we were taking the right side, going up till it hits the graph, then making a rectangle. And that was where we're getting our estimates. Well, what if we don't use the right side? What if we use the left side, the left endpoint? What changes? Well, it's not horrible, but it does require some adjustment. So if I build my rectangles based on the left side, so I'm going to go from 0 to 4, and n equals 4. Okay? So I take the height of the left side and make a rectangle. Take the height of the left side, make a rectangle. Height of the left side, make a rectangle. Height of the left side, make a rectangle. Okay? Now, Notice anything different about this? Yeah, instead of overshooting the area under the curve, we're now going to be doing an underestimate of that area. So that's new. And if I try to do out my R1, R2, R3, and R4, okay, width, height, and area. I realized I wanted to do a little bit of extra oomph for the height. Alrighty, so the width is going to be b minus a over 4. In this case, it's 4 over 4. Width is 1. So width is 1. What do I feed in for the height of my R1 rectangle? Well, that height is, well, 0. It's what happens when I feed in x equals 0. So the area of the first rectangle, 0. Okay, now I feed in the left side endpoint to get my height. So that's going to be f of 1, which is 1 squared, which is 1, which is 1 times 1, 1. So that rectangle has an area of 1. Then I move to my R3 rectangle. What do I feed in for its height? Well, I feed in x equals 2. That's going to be 2 squared, which is 4. And then finally, for R4, I feed in x equals 3 for that height. And that's going to be f of 3, which is 3 squared, which is 9. So 1 times 9, 9. Okay? So what do I get? I get an area estimate of 1 plus 4 plus 9, 14. That is an underestimate. Okay? And this would not be all that interesting, except something fundamental has to change with how we calculate our heights, because we're no longer feeding in the same values. When, here's a little shortcut, r of 1, let's do a little chart. What is the x value I fill in? Well, for R1, I fed in 0. R2, 1. R3, 2. And R4, 3. Alright, so what is the relationship between the rectangle number and the x value? 1 to 0, 2 to 1, 3 to 2, 4 to 3. Exactly. It's minus 1. So this relationship is no longer I, it is I minus 1. Okay? So I'm going to have to make an adjustment. My right endpoint formula was the area is equal to, or approximates, the summation I equals 1 to n of, I had b minus a over n times f of b minus a over n I, right? But the left endpoint formula now is going to be slightly different. The area is going to be approximately summation I from 1 to n of, that's an n, b minus a over n times the height, which is now going to be f of b minus a over n times I minus 1. Oops. Let's see if I can do that again. Boom. So the only thing that changes is this I becomes an I minus 1 if I use the left endpoint. Okay? So let's try that and see if we can get a general formula for this function and see how it compares to the right endpoint one. Okay, so let me clear this, and keep in mind the only thing that changes is that I becomes an I minus 1. So clear this, and so now my area is going to be approximately summation I from 1 to n of, well, b minus a is 4, right? So 4 over n times, well, this is f of 4 over n times I minus 1. That's a lot of parentheses. Okay? Should have done a bracket. That's it. That's all that's going to change. So this is going to equal summation I from 1 to n of 4 over n times, here we go, bracket, f of 4 over n I minus 4 over n. And there you have it. I just distributed, instead of 4 over n I, like I normally do, I have this minus 4 over n part right there. So I can work with that. That's not too bad. It actually only changes things a little bit. So let's see what we can do. A lot of math, but that's okay. That's what we're here for. So I'm going to have, this is the summation I from 1 to, actually, do you mind if I move that 4 over n out? That's going to bug me just sitting there like that. So 4 over n summation I from 1 to n of, well, what does this become? Well, do some scratch work right over here. My function is x squared, right? F of x is x squared. So what does f of 4n I minus 4 over n become? Well, it becomes 4 over n I minus 4 over n squared. Alrighty, so that's what's going to be over here. I'm going to have, if you will allow me to do that, the height now becomes 4 over n I minus 4 over n quantity squared. Okay? Now, I'm going to do something to make this look not so horrible. So this is going to be 4 over n summation I from 1 to n of bracket. I can factor a 4 over n out of here. So second bracket, if you will, this is going to be 4 over n times I minus 1 bracket squared bracket. All I did was I took and factored out a 4 over n out of this square here. And that's completely legal because it's still within the square. The 4 over n didn't move outside the square. But it lets me do something a little bit easier, rewrite this quite a bit easier. So what I can do now is say, well, that's equal to 4 over n summation I from 1 to n of, here we go, bracket. This piece is going to be 16 over n squared when it gets squared, right? So this is going to be 16 over n squared times, now I just have to do I minus 1 squared. So what is I minus 1 squared? Well, that's just I squared minus 2I plus 1. See how much easier it is taking this piece out, this common factor? Way, 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 way easier. So now this 16 over n squared is a constant, so I can take it out as well. So this is going to equal 64 over n times the summation of I squared minus 2I plus 1. Okay? Now, and that was n cubed, right? Don't forget the cube part, because it's an n squared times an n. Alrighty, so now I can break it into multiple pieces and get 64 over n cubed times, we're going to have bracket, well, I forgot to my subscript, 1 n. So summation I equals 1 to n of I squared minus 2 summation I from 1 to n of I plus summation I from 1 to n of 1. Whew. So what does this become? Well, I think I should probably clear the page. I'll do one more and then I'll clear it because I'm going to run out of room. There's no way I can finish this up on one page. So 64 over n cubed times, ooh, this is going to be a lot of stuff. Well, I squared evaluates into n plus 1, 2n plus 1 over 6 plus, or sorry, minus, that is a minus sign right there, minus 2 times n plus 1 over 2 plus n times 1, n. All right, we're getting there. Let me clear this and we will continue. So we have the area is approximately, we've got 64 over n cubed times bracket. This was n plus 1, 2n plus 1 over 6 minus 2n plus 1 over 2 plus n. Okay, now we can evaluate all this. So the area is approximately equal to 64 over n cubed, which is going to be this one evaluated into, was it 2n cubed plus 3n squared plus n, I think is what we got, over 6. And then if y'all will allow 2 over 2 is going to go away. This is going to wind up being minus n squared plus n, and then plus n. Okay? Now, let's see. Let me start getting this a little simpler. So 64 over n cubed times. Alrighty. This is going to be, well, I can't really do a lot with this. 2n cubed plus 3n squared plus n over 6. But this one is minus n squared, and then minus n plus n. Those two pieces are going to be gone. So I get that expression right there. All right, I can now, if I want, do a common denominator, because that's not too bad of an adjustment to just adjust that. So this is going to be 64 over n cubed times, I'm going to have 2n cubed plus 3n squared plus n over 6 minus 6n squared over 6. All I did was just make a common denominator so I can now subtract them. So this is approximately 64 over n cubed, and then I'm going to have 3n squared minus 6n squared, so it's going to wind up being 2n cubed minus 3n squared plus n over 6. Almost there. So that can become a 3, and that's a 32. All right, so it's now time to kind of distribute things. I'm going to have 32 over n cubed times 2 over 2n cubed. The n cubes are going to cancel. One will be left with 32 times 2 is 64 over 3. Okay, and then minus 32 times 3 over 3, so those 3's will cancel. It's going to be minus 32 over n. And then 32 times n over 3, and then you have to also divide by the n cubed. So this is, I can't really do a lot with this. It's going to be plus 32 over 3n squared. Alrighty? So let n equal 4. Okay, n is 4. We get 64 over 3 minus, this is 32 over n, so I'm just going to do 32 over n, so 32 over 4 plus 32 over, this is going to be 16 times 3 is 48. I think that's right. So 48. Oh, 32 over 48. Yep. Wow. Alrighty. So I need to multiply to get common denominator of, is there anything lower? No, 48 is going to be it. So I have to multiply the 64 by 16. So this is going to be 1,024. I've already done the work, so it looks like I could have just not said anything and just thought, wow, he can multiply that fast. No, I did it on scratch work just a little bit ago. So now to get this one to a denominator of 48, I need to multiply the top times 12, which is going to be minus 384 over 48 plus 32 over 48. And when the dust settles, we are left with 672 over 48, which reduces to 14, which is exactly what we found when we did it with the rectangles. Alrighty, now let n go to infinity. So this is going to be the limit as n goes to infinity of, we've got 64 over 3 minus 32 over n plus 32 over 3 n squared. Well, this term goes to 0, this term goes to 0, and we're left with 64 thirds. If you remember, when we did the right endpoint with that function, and we took the limit as n goes to infinity, we got 64 thirds. So it doesn't matter if you do the right endpoint or the left endpoint. When you take the number of rectangles to go to infinity, you are still going to wind up with exactly the same answer, and it is the actual area, which in this case is 64 thirds. Alrighty, so, I know that was a lot. For homework, and this was just for the left endpoint, it was a lot more stuff because you have that I minus 1 factor. I'm okay if you've used the right endpoints for just about everything. But it's nice to see how the left would work. Homework, do number 29 again, the same one we just did, except now use the left endpoint. Okay, use that formula. And just go for n equals 4 and n equals infinity. So the formula is exactly the same as the one you used before, except instead of your b minus a over n being multiplied by I, it's going to multiply by I minus 1. That's what you're going to feed into your f. Alrighty? So do the left endpoint with the same problem as you did last time, and now do n equals 4 and n goes to infinity. That should be it goes to. Alright, good luck, and I will see you later. Take care, stay safe.